Okay. So some things that you need to know in 8.4. You need to know how to find period. You need to know how to find amplitude. And you need to know how to find frequency. Out of these three, which is the only one we haven't talked about? Okay. Frequency is really easy. In fact, if you've done physics, you already know. Anybody remember? It's 1 over the period. Very good. Okay. Frequency is just another way of saying how many cycles of the trig function have elapsed per 1 unit of time. The unit of measurement is called a hertz. Okay. But basically that's the only thing that's new. The rest is just finding all the details out, graphing what's going on, looking at the picture, and answering some questions, which I think we can all handle. Okay? So let's look at this function they give you. S equals 6 times cosine of pi t divided by 4. S is your y, t is your x, or what used to be x. They tell you that t is in seconds, and s represents the position. So let's go ahead and look at this equation. What is the amplitude? Let's do that first. 6. The period would be 2 pi divided by b, which is 2 pi over, what's b here? It's actually the whole thing, pi over 4, which makes things nice because when you multiply by the reciprocal of pi over 4, which is 4 over pi, yeah, you just get 8. Okay, and from the 8, that's where we get what scale we're going to count by, right? What do we do with the period? You divide it into 4, so our scale is that we're going to go up or increase by 2 units. Okay? So the graph, since there's no phase shift, right, is actually relatively easy to graph. This is a cosine graph. Where does cosine start? Well, in this case, 6, but yes, I know what you meant. So we're going to start here at 6. And then as time goes on, we're going to go to 2, 4, 6, 8. And I'm going to actually graph 2 periods. 10, 12, 14, 16. So we start at 6, and then cosine goes down, back up. So you just fill in the points and draw your best cosine graph. And obviously this continues, but this is just one small snippet of what's going on. Okay? Now, this position right here, this x-axis, this is what we call equilibrium. It's like it's a resting position. So if you actually imagine, here's a spring, and I attach some kind of mass to it, this string is going to get, stretched out, right? A little bit. Do you guys understand? Okay. This is what S equals 0 means. So after you attach the mass, the resting position is S equals 0. So that would be like right here. But what's going on, according to this, is that we're actually compressing up 6 units. So that's where we're starting, right? You guys kind of see that? And then we're letting go so that now this mass goes down and then back, and in a perfect ideal world, this thing just goes back and forth from 6 to negative 6. Does that make sense? Okay. Any questions on... Oh, we didn't find frequency. Let's do that. So if the period is 8, then the frequency is 1 over 8. Pretty easy.
Where on the graph is frequency?
It's not on the, it's not technically on the graph, but I can show you with a different color. in 1 second, that's not a different color. I just picked a random pen and it was the same one. So in 1 second, how far along is this green dot out of the entire cosine graph? That's 1/8 of the way through the cycle. So that's what it means. So in 1 second, we've only traveled 1/8 of the entire period. Does that make sense? That's a good question. It's not really, it's hard to see, but that's what it means. So in 1 second, how much of the period has actually been gone through? Okay, so the shorter the period, the larger the frequency. Any questions on that? Okay. So, I mean, like I said earlier, now it's just answering the questions. So, part B says, at what times is the mass furthest from its equilibrium point? So, if equilibrium is the x-axis, where is it furthest from equilibrium? When it's at what height? Or, very good. So, this point here, this point there, this point there, this point there. Those are the points when it's furthest away, right? But now, the question is what times, right? So what's the time value here when it's up at 6? 0. And what's the next time value when it's far away? 4, and then 8, and so on and so forth. How do we write this nice and neat? We say when time is 0 plus 4k, and now we're going to do something really, I think it's kind of cool, but I'm also a math nerd. Instead of saying any integer, we're going to put a little plus sign next to the z, which means that we're only doing positive integers because we're not going back in time here. Okay? So this really means that we're adding 4, 8, 12, 16, and that represents all the different times when the mass is 6 units away, which is the furthest it can possibly get. Does that make sense? Okay. Next question, at what times, so again it's looking for t, is the mass passing through equilibrium? Well, visually on the graph, that's just what? The x-intercepts. Very good. So that would be when time is 2, what else? 6, 10, and so on. So we could say t is 2 plus 4k.
Why does it start at 2?
Because that's the first time it was 0, right? So where k is any positive integer. Make sense so far? Like I said, we know how to do all this stuff. It's just now we're actually applying some real-life terminology to it. Why don't you guys... So now we're going to graph the velocity. And here's the equation. We're going to do this one. So what we're going to graph, and this is actually what you would do in calculus. In calculus, you'd get the first part of the problem given to you, and then you'd have to actually come up with this equation on your own, because they might ask you, what's the velocity of the mass as it vibrates back and forth, and you'd come up with this equation on your own. Now, you don't have to do that, obviously, but next year you will. Right now, I will tell it to you, and your job is to simply graph it, look at the graph, and answer the questions. Okay? So let's get the graph started. What is the amplitude? Amplitude is never negative. The negative just means that the graph flips over the x-axis, right? So amplitude is 1.5. Period is still going to be 2 pi over b. It's the same coefficient from part A, right? So can we just write down 8? Are you guys cool with that? And then the same scale. So let's graph. Oh, wait a minute. I messed up. The amplitude is not just 1.5, it's 1.5 pi. Which looks kind of weird, but it doesn't change what we do on the graph. That just means that we're going to put 1.5 pi and minus 1.5 pi for the y-axis. This is and we're going 2 periods. Let me label that. 2, 4, 6, 8. That's 1 period. 10, 12, 14, 16. And, okay, we should be good to go. This is a sine graph. Where does sine start? 0. And now, if it's negative, rather than going up, it's going to go down first, and we just connect the dots. So actually, you can compare. This is called a position graph. This is called a velocity graph. This is t with velocity. This is t with position s. Okay. At the start of this model, when we compress the spring, okay, right when we let it go, does it make sense that it's got no velocity initially? You guys are looking at me with blank stares like, what the heck are you talking about? Okay? Imagine an actual spring and you push it up, right? The instant when you let it go, does it have any speed or any velocity? No. As soon as you let it go, though, what does it start to do? It starts to move faster. Okay? And now what's happening is it moves in the down direction, which is why the velocity is negative. Okay? So now one of the questions they ask is, when is the velocity equal to 0? So let's look at our graph. So if this is velocity, where's the first time that the velocity is 0? At 0, where else? 4, 8, and so on. So we're going to say when time is 0 plus 4k, where k is any positive integer. And there's a second question here.
Wait, what do you write above the Z?
Plus sign.
Plus.
The second question is, where is the mass at these times? Okay, so for this question, where means not velocity but position, right? So we're going to look back at our position graph and look at the times 0, 4, 8, 12, right? Where was the mass? Up at 6 or negative 6. So we're going to say the mass is at its, and actually the answers are right here. So look at part B. What do they ask us to find? The times where the mass is furthest from equilibrium. You see how our answers were 0, 4, 8 up here? We're just going to reword the same thing now. So mass is at its furthest point from equilibrium. Okay. You guys good with that? Kendall, at what times is the velocity a maximum?
High points and low points.
Which would be what times?
0 plus.
So we're starting here?
Oh, my bad. 2 plus 4k.
Yes.
And all positive.
2 plus 4k, where k is any positive integer. And what he was saying is that at all the high and low points,
Oh, my. Yeah.
that's when the velocity is at a maximum. Okay. Justin, what's not a maximum?
2 is not a maximum.
Why?
It's negative.
Very good. So we're almost there. You're half right. This is a minimum value, right? So the only ones we actually want to include are 6, and then the next time it's at 6, which is 14, right? So let's clean this up. So when time is 6, 14, and so on, what's the pattern? There we go. So we're going to say 6 plus 8k, where k is any integer. And now the last question is, where is the mass at 6 and at 14? So at 6 and at 14, the mass is at 0. What is that called? Equilibrium. Very good. So mass is at equilibrium. Okay, so this is just one little simple application of sine and cosine graphs. Sorry. One little application of sine and cosine graphs now that we've been graphing these for a while.